So here's our theorem about pointwise limits of measurable functions. So let X be a measurable space, sigma algebra fancy A, and let's suppose you have a sequence f sub n of measurable functions, so measurable real valued functions, and assume that f is the pointwise limit. So this is our notation for pointwise limit of a sequence of functions. Then we claim that f is measurable. So this is a pretty, maybe this is a surprising conclusion if you're used to the idea of pointwise limits from 118b, because we always talk about how things just don't work for pointwise limits, and you really need uniform convergence for sequences of functions to get things to work. Like, for example, with continuity, a sequence of functions can converge pointwise. A sequence of continuous functions can converge pointwise to a discontinuous function. But if you demand uniform convergence, then you can show that the limit has to be continuous. So that was our continuous limit theorem. But look at what's going on with measurability here. Pointwise convergence is sufficient to conclude that the limiting function is measurable. So that's pretty strong, pretty nice. And we will basically do the proof by hand. I guess we're doing all of them by hand, kind of, but I mean in a way that more closely uses the definition of measurable function rather than relying on trying to break things up into being a composition of measurable functions. Okay, so let C be any real number. So this is what I mean by using something close to the definition of measurable. So remember, for a real valued function, for it to be measurable, what you need to show is that the preimage of this kind of set is going to be in here for all C. That's what we need. This is sufficient. You don't have to work with arbitrary Borel sets. It's enough to work with these guys, since these guys generate the Borel sigma algebra on R. So this is why we're fixing C in R, is to try to show this. So now I'm just going to write down a statement that will that if we verify that it's true, we'll see that that preimage is a measurable subset of X. And it'll be a long statement, and then we'll verify it. Okay, here it comes. Okay, so the statement is that then the preimage of this set, the collection of points in X that F maps to numbers that are less than C, can be described in this way. It's the union over all K of the union over all capital N of the intersection over all little n bigger than or equal to capital N of all of these preimages. And this is something that we're going to verify. But first so instead of putting a period here, let me put a colon. So colon indicates that I'm about to prove this assertion. But how does this help? Well, if we do this, then we're actually done. Because these are all in A, right? These are all in fancy A, because the FNs, the individual FNs, are assumed to be measurable. And so when I take the preimage of any set like that, it's in fancy A. So in other words, these are all measurable subsets of X, of big X. An intersection, even an infinite, a countable intersection of measurable subsets of X, that's going to be a measurable subset of X. So this is in A because sigma algebras are closed under countable intersection. This is in A because sigma algebras are closed under countable union. This is in A because sigma algebras are closed under countable union. So if we do all of this, then we will have that this is in A, which is all we need to show that F is measurable. So all we need to do is prove this equality. So I'm just going to do it by proving two equations. And if you want to try this yourself, it's actually pretty fun. So if you're interested in trying it, don't let me ruin the fun. You can stop the video at this point. I'm not going to do anything else for this video other than finish this proof, and just try to do it yourself. But also, if you want to just view me doing it, then go ahead and do that. Okay, so let's see. Suppose x is in the left-hand side. Then what that means is f of x is less than c, right? Now, what do we have that we can use about x? Well, we know that this sequence of functions converges to f pointwise. So that means that we do have that at x, at the point x, this sequence converges to f of x. So let me draw a picture here. I've got f of x is less than c, so here's c somewhere on the real line, and here's f of x. And f of x is strictly to the left of c. And what am I trying to prove? I'm trying to prove that there exists a k such that there exists a capital N, such that for every little n bigger than or equal to capital N, f sub n of my little x is less than c minus 1 over that k. Okay, so when I phrase it that way, maybe it's a little bit, seems like a lot, but the point is basically just to look far enough in this sequence, f sub n of x, look far enough down the sequence that your terms of the sequence are well away from c, well to the left of c. So since I know that this sequence of real numbers, the fnx's, so these fnx's, is a sequence of real numbers, so it's a bunch of dots here, eventually it's going to converge here, right? So eventually, for any given open set that I put around here, it's going to enter into it. So then let me put a little window around f of x that whose right part definitely is strictly less than c, so like between f of x and c. And I'll choose that as my kind of epsilon for my epsilon window. So the exact midpoint here might be f of x plus c over 2, something like that. That is the exact midpoint. But actually what I care more about when I'm choosing my epsilon is the distance from here to there, which is going to be c minus f of x, this distance, over 2, if I take half the distance from between c and f of x. And my window is going to be a little bit smaller because I'm after the existence of a k that makes some nice things happen. So I'm going to choose, for my next step, I'm going to choose k such that 1 over k is less than this positive number. This is a positive number because f of x is less than c. So Archimedean principle, there exists a k. Okay, so however k is chosen, 1 over k might be a little smaller distance, whatever, that's fine. So now I'm going to use that as my epsilon, kind of, in my application of this known convergence statement here. So then there exists a capital N such that for all little n bigger than or equal to capital N, the little nth term of this sequence is within epsilon, my choice of epsilon, which is 1 over k, of f of x, the limit of the sequence. So fn x minus fx less than my choice of epsilon, like that. Then, so what I'm really interested in about the fn of x's is to get them all less than c minus 1 over k, right? To ensure that x is in this preimage here. So then, let's write it like this. Let's see. So the fn of x's are guaranteed to be inside this window, and what I care about is that they're less than this green right parenthesis that I drew here. So fn of x is less than f of x plus 1 over k. That's one conclusion that you can draw from this inequality here, right? And 1 over k, the green thing, is less than the midpoint there, so that's less than 1 over k is less than this thing. So let me replace 1 over k by this strictly larger thing. And if you do the algebra, this should be the same as c minus this, right? Like if I start here and I add half the distance versus if I start here and I subtract half the distance, that should be the same. And if you do the algebra, it would be the same. And what I'm doing here is actually, so okay, yeah, this, I'm trying to get this less than c minus 1 over k, and I think it is because if you flip around this inequality, it tells you that minus 1 over k is greater than the negative of c minus fx over 2, right? And here we have the negatives. So this is less than this. Okay, so that should prove that x is in the right-hand side up here. To prove that it's in this infinite union of all k over all k, I have to prove that there exists some k so that it's in this thing. To do that, I have to prove that there exists some capital N so that it's in this thing. I've got a k and a capital N in hand, so all I need is to have that for all little n bigger than or equal to capital N, little x is in here. And we do now have that for all little n bigger than or equal to capital N, I should say this. I should have said for all little n bigger than or equal to capital N over here, since little n is under quantifier here. So for all little n bigger than or equal to capital N, we have this. So for all little n bigger than or equal to capital N, we have x is in this preimage. So x is in, you could say, the intersection of all of these. So x is in the right-hand side of, let's call it star. Let's call this equality star. Okay, so that's so much for that inclusion. Now let's do the reverse inclusion. So now assume that x is in the right-hand side of star. So then there exists a k, there exists an n, so let's get these k and n to work with, such that this is true. Then there are k and n, such that x is in this intersection, an intersection over all little n greater than or equal to big N. So we've got these natural numbers k and n to work with. So let's write this in simpler terms. What does this say about x? It says for all x is in every one of these, right? It's in the intersection. So for all little n bigger than or equal to big N, f of x is less than c minus 1 over k. Sorry, f sub n of x is less than c minus 1 over k. So now we've got the sequence of f sub n of x's, which converges to f of x, right? And we're saying for all n, past a certain point, past big N, we have this inequality, right? Now we can apply the order limit theorem. By the order limit theorem, we get this inequality for the limit. So basically I'm taking this inequality and then applying n goes to infinity, applying the limit, and applying the order limit theorem. And the inequality can become non-strict when I do that, right? But no problem, because I've got this 1 over k sitting there. So that proves what we needed, right? That f of x is less than c. So thus, x is in the set of things that f maps to something less than c, which is the left-hand side of star. All right, that was fun. So that's Theorem 215, Part 5. The pointwise limit of measurable functions is measurable.